This is the third talk in the Diving into Delta Lake series, and where we're going to talk about how delete, update, merge, these operations work in Delta Lake. We're going to take a little bit sneak peek into the internals of how do they work and how you can tune the performance of this. So I myself, TD, thank you, Karen, for the introductions. So a little bit background about myself. I have been working in the Apache Spark ecosystem since 2011. Back then, I was a grad student in the AMP Lab UC Berkeley, where in 2012, I along with Mati Zaharia, who started the Spark project itself, we started working on the Spark streaming. We built Spark streaming together, and now 8-9 years later, where I'm right now a staff engineer at Databricks and a co-developer of structure streaming and Delta Lake. And Denny, do you want to say a little bit about yourself?
Cool, thanks very much. I'm not as smart as TD, but I'm a staff developer advocate here at Databricks, working as a I worked with Apache Spark since 0.6, so roughly around the same time, around 2011 as well. Former senior director of data science engineering at Concur. I'm also a former Microsoftie, yeah, there you go. I think those are the key components here. So I'm glad to be here, and hopefully you'll enjoy today's session.
All right. So for those who are completely new to this series, this is the third talk of the series. So just to bring it up to speed, there's a one-slide intro on what Delta Lake is. It's essentially like an open source storage layer that brings ACID transaction to Spark workloads. So the format is open. You can store files in the same way as you would create Parquet tables. You can create Delta Lake tables. But unlike Parquet tables, where things can get bottlenecked on the metadata handling in Spark, with Delta Lake, the metadata handling is far more scalable than Parquet tables and other things. The whole table is versioned, so you can travel back in time and query earlier versions of the table. You get full-on schema enforcement and schema evolution properties, which ensure that you can maintain a much higher quality of data without corruptions and stuff, as well as you get the ability to audit all the operations you have done with transactional guarantees in the history of the table through APIs that allows you to query the history of the table. And fundamentally, how Delta Lake works is that it maintains a transaction log within the table, within a subdirectory called Delta log. It maintains a transaction log of all the operations that has happened. It maintains it by writing these JSON files, which has description of all the operations that happened, all the files that got added and removed in each of the operations. And so each of these JSON files is essentially like a new version of the table. And this log is maintained within the same directory where all the rest of the data files are also maintained. So all the information, both the data and the metadata, is co-located in one location, and this log is updated atomically on every operation. Therefore, you get full ACID transaction guarantees on any operations on the table. That's like a 2-minute version of what Delta Lake is. So if you want to know a little bit more detail of how this transaction log works, etc., go take a look at the part 1 of the series. YouTube link is here. It's also in the YouTube channel that you hopefully have subscribed to. And then if you want to learn more about the schema enforcement, which I have written the title wrong here, it's about schema enforcement and how schema validation works. That's the part 2 of the series. So in this part 3, I'm going to talk about DML operations, update, delete, and merge, how they work under the hood, and how you can tune the performance to get the best performance out of it. So, and I'm going to end by talking about some common design patterns we have observed that our users of Delta Lake have used, and how they can probably help your use cases as well using these DML operations. So the first operation we're going to talk about is update. An update is simply SQL update. Update table set x equal to y based on a predicate. And what we have provided is not just SQL support, but also Scala and Python APIs for doing this update operation. So now, incidentally, the SQL support is currently only available in Databricks Delta Lake, but we are really trying hard to get it out in the open source Delta Lake. but it will come out as soon as Spark 3.0 comes out, which has actual parser level support for these DML operations like update, delete, merge. So as soon as Spark 3.0 comes out, we will have a Delta Lake release with actual SQL support for these. Until then, you can always use Scala and Python for doing these sort of operations. And the way it works under the hood is that Delta Lake maintains these files. And so it only tracks data at the granularity of files. So what, let's say here, let's say you have the version 12 of the table where you have 4 files. Now, let's say you run update. What it will do underneath is that it will use 2 scans on this data to update them. First, it will do a first scan to files contain the data that needs to be updated based on the predicate that you've provided. So let's say out of these 4 files, 2 of the files has data that matches the predicate. Now in the entire file, not all the rows in the file, by the way, these are Parquet files, that's how Delta stores it, stores the data as Parquet files. So now not all the rows in the Parquet files may match the data. So there will be some rows that actually match the predicate, some rows that does not match the predicate, as you can see marked here as green and red. So now to identify these files, it uses the predicate and column stats and partitions, etc., partition pruning, all the things that Spark provides. It uses that to narrow down what files it needs to actually read to actually find that whether the file contains matches or not. Now, once it finds those files, it selects them and does another scan once again to essentially rewrite those files. So those 2 files got rewritten as completely new files because we cannot go ahead and update files. Parquet files are not designed for in-place update. So we have to rewrite the entire data in the Parquet files as new files where the data that matched, that did not, the data in the files that matched actually got updated, and the data that did not match got just copied into these new files. And the files that got replaced are essentially tombstoned, which means that in the transaction log, what we do is that we add this information that 2 new files got added and the files that got replaced were removed, marked as removed. They're not physically removed from the directory, so that we can do time travel, which I'll talk about later. We can still query those files as a previous version of the table. So underneath, this is what happens. So let me actually send it over to Denny, who can actually demonstrate this in a notebook and give a better, cleaner idea of how this works underneath. Over to you, Denny. Let me stop sharing my screen. Denny, we can't hear you.
It would help if I muted myself, wouldn't it?
Yes, would help.
It would help. Okay, cool. So I want to just make sure you guys can see my screen perfectly fine. This notebook.
Yes, I can.
Perfect. Excellent, excellent. All right. So exactly what TD was talking about, right? So in other words, we created this Delta table. So I'm just skipping through, and you'll notice that there are actually a bunch what the underlying file system looks like. So I'm just going to run it live so you can take a look. But basically, you'll notice that there's an underscore Delta log, and there's this Parquet file, right? And so this is what it initially looks like, just like what TD was talking about. Okay. I'm going to skip past what the initial log is and the metadata, though I'm leaving it in there so that way, from a standpoint of the notebook, you guys can have it for yourself. Okay. Now, here's what the data looks like initially. Okay. So basically, you've got a state. If I was to just explore the data, here's what it looks like. And you notice that Iowa's null and Washington has a value of 3.2. Okay, but now I want to run an update, just as TD was talking about. So let's go ahead and do this. In this case, I'm going to be rather arbitrary here, and I'm just going to say, hey, let me look at the number of loans that I want to go ahead and update. Okay, in this case, 209. I'm going to go ahead and in this case, run this update statement where I'm saying for the state of Washington, updates the paid amount to be equal to the funded amount. Okay, so in other words, I want those values to be updated. Okay, just as TD was talking about. All right, so with a Delta Lake, as TD not talked about, you can run an update. But then what's actually happening underneath the covers? All right, well, let's go look at the jobs real quick. All right, so for example, we have job 1838. Let's go look at that now. Sorry, all right. Okay, it's going to pop open. And we're going to, oh, sorry, I'm going to scroll back in so you can see it better. All right. So here's all the jobs I've been running here. Job 1838 is right here. We're going to write the transaction log. We're looking at the DAG visualization.
Go to the SQL query.
Oh, sorry. Yes, I meant to do that and forgot to do it. So there we go. Okay, perfect. So as you can tell, I want to zoom back in from the statistics. We read one file. Okay, it's written right here, actually in the Spark UI. Okay, so we've read one file. Here's all the information we did, like the cache write size, the time spent, file system, all these different things. But here's the rows output. Okay, and sorry, let me try to close that. So that's how it starts off with, and then let me go ahead and go back. And was it 1839? I think. There you go. So again, here's the 4 rows that are going to be set of rows that are potentially going to be impacted, and all the exchange processing and all it's actually going to go do to the data. Okay. Now, if I was to go instead, just simply look at the history of this, the operation metrics are actually embedded right inside here. Okay. So the total number of rows, 14,705. The updated rows, there were 340 rows, in fact, that were actually updated because we actually updated all of Washington State, not just the ones that were the values were separate, but we updated all of them because of the way I wrote that particular statement. And so the number of rows that were copied was right here, 14,365 plus 340 equals the 14,705 that you see. So underneath the covers, that's what we're doing. We're actually taking a copy of all the files into a new set of files. Okay, and we're going ahead and making the modification as you see here. So here's what the result looks like, right? Where I just simply said Washington State's null. And then when I look at it, see, here's the file right here that you see. Okay, so this is the file that actually has the new set of data per the updates that just happened. Okay, cool. TD, let me switch it back to you so you can go ahead and flip to the next section.
All right.
Perfect. Bam.
All right. So now that you have seen how you can create new versions by updating the data, you can still go back and query the old version. So Spark Delta Lake provides these ways to query previous versions of the table that you saw in the history. So here, if I had created version 13 by updating version 12, you can still query version 12 using this option called version as of 12. And so now you can just compare, compare 2 versions of the table very easily to see how the rows got updated, if there was incorrect update, how you can debug it and stuff like that. So that gives a lot of power to actually go back in time and figure out what happened, whether all the updates that happened were correct, or if you see some sort of corrupted data, you can go back and check in which version did the data get corrupted, and maybe roll back by reading the version, overwriting the table with the correct older version once again. So this is again a very powerful tool. So now let's talk about how do you improve the performance. So as Jenny showed you that there are 2 scans on the data. Now somebody asked a question regarding whether those are 2 full scans or not. The simple answer is that the first one may be a full scan, but the second one is usually not. So it all depends on what predicate you put. So if your predicate, for example, say that update all the rows in a particular partition, then the first scan to find all the files that needs to be updated will only query that partition. So it doesn't need to do a full scan. However, for example, if your table is not partitioned, it's a relatively smaller table, therefore not partitioned, it can be that it cannot narrow down based on your predicate what files to look at, it will, in that case, will have to scan the entire table to find which files have matches that satisfy that predicate. But after that, that's for the first scan. But the second scan usually scans over only the files that needs to be updated. And so, so to answer this question, it doesn't have to be 2 full scans. It completely depends on your table setup. But now the key thing to remember here is that the more predicates you add in the update clause, the better it is, the easier it is for Delta Lake to narrow down the search space, and therefore the faster that first scan is going to be. So that improves the total runtime of update. Now, the Databricks Delta Lake platform has a few more performance optimizations. That's the difference between OSS Delta and Databricks Delta Lake, is that we have a little bit few more performance improvements in Databricks Delta Lake. There are tools for doing better data skipping, especially we have this thing called Z-order optimize that essentially can optimize the layout of the data in the table in a more complex, more organized manner. It's essentially like multi-column sorting, but much better than that, using space filling curves and stuff. And so it essentially improves the efficacy of storing column stats at the level of files and stuff. And then there's also support for Bloom filters. We will not go into detail of those, but the key idea to remember is that if you really understand what goes on underneath these operations, it makes it easier for you to reason about how to optimize the performance of these operations. Like, for example, narrowing down the search space by adding more predicates if you know where your matches are going to be present. So, similar to update, there is delete, where similar syntax, delete from table based on predicate. There's obviously SQL that is going to come with Apache Spark 3.0, but there's, until then, there's also Scala and Python support directly in. But it's interesting to remember that, as Denny showed, that the update doesn't creates new files, but it doesn't replace the old files. It only marks it as tombstone. It marks it as deleted in the transaction log, so that it doesn't automatically delete it, so that you can do time travel and query those old data once again by specifying the exact version number. But now for deletion, the setup is exactly the same. Any data that needs to be deleted will rewrite new files, but the old files will be preserved by default, so that you can go back and query the version of the table before the delete. If things get accidentally deleted, you can roll back and stuff. But in some cases, you actually do want the data to be completely permanently deleted from disk. You don't want any file to have the old data. So for that, you have to run this additional operation called vacuum. That's an operation that is specific to Delta Lake. And what it does is that you can say how many previous, or what is the length of the previous versions that you want to retain. So let's say you want to retain all the versions written in last 1 day, because you know that you don't want to care about querying any version of the table that is older than 1 day. Then you will run vacuum table retain 1 hour. By default, if you don't specify the retain, it is 7 days. That's what we have observed and works well in most situations. But what it goes ahead and will do is that it will figure out what are all the files present in the directory that are not needed by any of the versions present in that were written in the last 1 day. So any file that is not needed in the versions written within the last 24 hours, those will get deleted. And that includes any sort of partial files, corrupted files, etc., that may have been written but not actually committed to the log because of failed writes and stuff. So vacuum will delete all of that. And using that, you can actually control how much of the previous versions you want to retain and what you can delete. And eventually, you can age data out from all the data files in this way. The data will actually get deleted. So you can even run vacuum retain 0 hours. That actually will keep only the latest version of the table. If you really don't care about history and you really want to ensure that after deletion, all the data has actually been physically deleted, you can run vacuum retention 0, which will preserve only the last version. However, it's important to remember that vacuum 0, do not run vacuum 0 when other writes are in progress, because you may delete files that are being currently written right now. So just be careful of that. Anyways, so then on to merge, which is probably the more interesting and most powerful operation among these three. So merge has a standard SQL syntax, has a standard SQL and SQL syntax, where the idea is that you are merging into a target table using data from a source table, where based on a match, that if you match the keys of a source row and a target row, if it is matched, then you can update the column using the matched source data. If there is no match, that is, if there is a source row that does not match any target row, then you can insert a new target table column based on the source, new target table row based on the source row. Now, this is standard SQL syntax. We support that, obviously, but we have additional support for a lot more extended syntax that makes things a little bit more interesting. For example, we have support for additional clause conditions. Say that, for example, you have matched based on this condition, but you want to have additional condition on top of those matches. Then here you can specify additional clause conditions, not just the match condition, but clause conditions that needs to be satisfied before the update kicks in. And similarly, when not matched and additional clause condition, then only insert would happen. And where this is useful is that you can actually have multiple, at least up to 2 matched conditions as well. So, and you have support for deletes as well, which the ANSI SQL syntax doesn't. So here you can say that when matched and clause condition, then update. Otherwise, with it, given if it's matched, then but the clause condition not satisfied, delete. So you can, and this is very powerful, as we will show in using examples later, to do a lot of complicated changes within the table. And we're going to walk through a few use cases where this is very, very useful. The other very useful feature is this star support to auto expand target columns. And this is, as far as we know, the only engine that supports this sort of a syntax, which is once we introduce it, was a very, very popular syntax. What it does is essentially for a table with a very large number of columns, you do not want to handwrite all the columns that you need to update. Let's say if you have a bunch of changes which requires you to update all the columns if it matches, or if you want to insert all the columns with the exact same as a source, then you don't want, it's often tedious to handwrite all the columns if the number of columns is in the range of hundreds. So update star just essentially auto expands the columns to say that update set column 1 equal to source column 1, column 2 in target equal to source column 2, just auto expands, which makes it much easier to just express and actually manage this sort of queries. So we also have support for programmatic APIs, Scala and Python. Again, one of the very few systems we know of that has actually programmatic APIs for doing this sort of SQL merge operations. But it's I think, depending on what kind of user are you, as a primary SQL user or a primarily programmatic software engineer, data engineer kind of person, which I'm more like that. I like type safety. This is very, very, very useful. So under the hood, what happens is essentially the exact same thing as update. There are 2 passes on the data. One to find the list of files that has matches and therefore needs to be updated, and a second pass to update those files by rewriting them as new files. But the interesting bit is that now, unlike update and delete, here in both cases you have to do a join between the source and the target to actually find the matches. The first scan is essentially inner join between the target and source. to find the match. The second one is an outer join between only the selected files in target and the source to generate, to do the update, delete, insert operations on the data on those files. And again, some of the data may be copied, some of the data may be updated, deleted, inserted, etc. Again, Denny will demonstrate this much more effectively than me. Over to you, Denny.
Thank you, sir. And this time I actually bothered remembering how to go ahead and unmute myself. So that actually usually helps. Cool. All right. So exactly what TD was talking about. And by the way, don't worry. I've asked you folks to go ahead and ask your questions in the Q&A panel. It's not that we're not willing to answer them. It's just that we're going to most likely answer some of these questions after the session, once we do the regular presentation portion of it. Okay. So, all right. So here's just a quick animated GIF about the insert update / process when you're running a merge, right? So typically underneath the covers, basically what we're doing, just like TD had called out, you identify the new rows to be inserted, identify the rows that need to be replaced, i.e. updated, identify the rows that are not going to be impacted by the insert, the update, create new temp tables, delete the original table, rename the temp table, and drop the temp table. Now, that's if you were to do it under the regular Parquet process, right? So it's pretty inefficient, and it requires you to actually do all the writing. And I'm lazy, so I don't want to do all that writing. So that's why TD shows this awesome merge syntax, which actually simplified that process massively. All right. So in other words, when I do that, I can just simply write a merge statement. Okay, so let's use a quick example here. I'm going to go ahead and take a look at some data here. Okay, for example, if I was to look at just New York with loan ID less than 30, this is the 3 rows that I have here. Okay, in terms of what that could potentially be impacted. Okay, I have a loan ID of 11. 21, 28, each of them being funded with about $1,000 to $1,200. Here's the different paid amounts and the state being New York. All right. Now, let's create a new table that we want to now run the merge. Okay, so remember, the first table is the source table. It's of the 14,705, 3 rows of the 14,705 that potentially can be impacted. Now, here's this new table that we're creating, which is listed here. We're basically for loan ID 11, for $1,000, we're going to go ahead and pay it off, right? That's this first row that you see here. Okay, so that's why the funded amount is 1,000 and the paid amount is 1,000. Okay, all right. So then we're also going to add a new loan. Okay, and we're also going to, for the fun of it, also add a duplicate loan. Okay, in other words, by accident, the source system screwed up, so there was a duplication. All right. So again, as opposed to going ahead and running all of those other statements where I'm going to do an insertion specifically for loan ID 12, I'm going to deduplicate the data myself for 28, and I'm going to go ahead and run an update specifically for loan 11. I'm just going to run a single merge statement, and it's really simple right here. Actually, it's right here. Okay. And so I'm using the Python syntax because unlike TD, who loves type safety, I'm lazy, so I don't like doing it. No, I'm joking. I just happen to like the Python language, that's all, even though the tabs irritate me a lot. Nevertheless, I'm going to simply do a merge where basically it's where the source table, s.loanid, is equal to the target table, t.loanid, okay? Where you basically, when it matched, you update them all. When not matched, you insert them all. And then implied inside here also is the deduplication as well, okay? So same idea, we have a bunch of stages, okay? Now, there's one question in terms of that was asked, which I'm going to answer right now, which is about the execute plan query, query tool costs. Okay, that's actually what the Spark UI is for, right? It actually provides you a lot of that context. So I'm going to look at 1844 using the SQL tab, just as TD had called out. So I'm going to go look at this, right? When I look here, the query plan is actually before I even show you the DAG here, let me do a quick call out. The logical plan is actually listed right here, so you can actually understand logically what Spark's doing underneath the cover. So you can actually go ahead and see, similar to your, when you're working with a relational database, you have a logical plan, same concept. All of that's actually placed right here. Now, obviously, some people are going to turn around and say, but I'd love to understand how it works graphically. And then that goes back up to here, right? Which basically the timing is here, 7 milliseconds for the whole stage code gen here, so 1 second for this particular whole stage code gen, in order for it to do its various processes, okay? So a lot of your query information is actually all in that Spark UI. So you can figure out how to improve the performance by understanding what's going underneath the covers. So for example, this one implied right away. Actually, you know what? I'm going to go look at a different one right away. Give me one second.
This is actually the inner join.
Exactly. I want to talk about the other one first. So okay. I think it's this one.
Yes, the 45 that should be the one.
There you go. Perfect. 1845. Okay. So here is that sort merge join, right? So in other words, here's the two files. Okay. So for example, when you open this one up, okay, it tells you right away 17 milliseconds was taken to read a single file, right? And that file was the file that contained the 14705 rows of data that we were working with, okay? And so in fact, it actually tells you right here. It tells you about the cache, the file system reads, and all these other statistics, which actually helps you understand why the query performance is going to be that particular way. But it lets you know right away. So exactly as TD was explaining about, like, you know, the number of files or partition, right? You will be able to tell, like, if this is running in seconds or minutes, like a very long time, perhaps partitioning needs to come into play because you need to go ahead and reduce the number of files that are going to need to be read. Because for sake of argument, you're only trying to process one state or one date of data as opposed to 3 years of data, using that as a simple example. Okay. All right, let me close this up. There we go. All right. So then versus this scan existing RDD, that was the 3 rows that we created. Remember, we had created this loan updates table. Well, this is what the scan our existing RDD is. Again, this is a small idea, but here's the projection that you can see it right here. The loan ID, the funded amount, the paid amount. This is the RDD that we explained, right? Then exactly what TD was talking about in terms of the joins that happen. Here's that sort merge join that actually had to kick off. So first there was a sort, right, of this information. And then now we're going to do a sort merge join between the 3 rows that we originally had from the table that we generated, that we created, versus the 14705 rows that came from the Parquet file, the single file that we had in this case, that we would now perform the join. And then all of the statements, the projections here, right here, right, in terms of how it figures out the logic, that's actually all shoved inside here, okay? And so the idea is that underneath the covers, then you can tell right away what's actually happening to the data, okay? In other words, it's grabbing one file, it's grabbing the 3 rows, it's going to do a sort merge join. That's what this example tells us. Versus the previous step, 1844, I believe. Yes, here we go, right? This is actually doing a broadcast exchange, right? In terms of here's the amount of data that's being pushed over, right? That tells you the data size itself actually helps you understand, okay, if you've got a ton of data that's being broadcast or exchanged over and over again for this broadcast hash join that's happening right here, yeah, this tells you that you're probably transferring or shuffling or moving too much data across the wire, right? So again, can you shuffle? Can you filter? Can you partition to reduce the sizes that you're working with? Okay. And then ultimately, back to this again, we look, for example, the output of this is when I look at New York, there's the loan ID 11, which is basically the one where we updated it, right? Here's loan ID 12, which basically is the brand new one that we just added. And here's the other loans that basically were unaffected, right? In other words, we actually put a duplicate 28, but the duplicate never actually entered in there because the merge statement automatically had deduplicated the data, okay? And then same idea, when I would look at the history, right? I can look at the metrics, right? The operation metrics are right within the history. So you know how many rows were copied. In this case, of the 14705, 14702 were actually copied, okay? We only looked at one single file in order to make sense of it. The target rows that were updated, 3 of them were actually updated, and based on the source rows of 3. Whoops, sorry. There we go. Okay, and the number of bytes. So all that information is basically packed inside basically the operation metrics that you see within the history table and within the Spark UI, the SQL tab, to basically make sense of from the UI perspective. Cool. Hey, TD, anything else you think I should be adding, or we're good to go here?
Yeah, I think we're good to go.
Okay, perfect. All right. Well, I will stop sharing now.
Awesome. Awesome. All right, let's talk about how we can improve performance. Okay, let me have it, please. Oops. Yeah. Let's talk about how we can improve performance. So it's important, because I said with update, it's important to understand what goes on underneath the covers. As Denny just showed you, there's an inner join and there's an outer join. So you have to really understand that what is the bottleneck between the inner join and the outer join. If the inner join, which is finding the files to rewrite, is the bottleneck and taking the most time in the query, then you have certain optimization techniques. If it's the other one, then you have a certain other optimization techniques. So if the inner join is slow, that is, you're taking a lot of time to just find the files to update, then again, the standard techniques of adding more predicates into narrow down the search space helps. You can obviously adjust the shuffle partitions. These are standard Spark optimization techniques. Adjust number of shuffle partitions to control the parallelism of the shuffle that needs to be done for the join. You can adjust the broadcast join to tweak it towards broadcasting it, allow larger data to be broadcasted if the source is small enough to fit in a single machine memory. If there are, sometimes it slows down because there are too many small files in the table. Like if you have a million of teeny kilobyte sized files, then the overheads of reading each one of them is much higher. Then you should compact the delta table. There is online documentation on how do you rewrite the layout of the delta table to compact them. But then again, you shouldn't make extremely large files like 10 GB files, because you have to remember that we rewrite only at the granularity of files, and the larger files that you create, the more data may need to be rewritten unnecessarily. So if there is only one row that needs to be updated in a file, it's cheaper to rewrite an entire 100 MB file rather than a 10 GB file for that one row being updated. So you have to tune that based on your workload's requirements. And then again, Databricks Delta Lake has few performance optimizations. The Z order optimizer that I mentioned earlier helps to sort the data in smart ways, which allows you to exploit the locality of updates. That if your changes are going to be in a certain range of values only for a particular column, then you can Z order optimize by that column to get better locality, so that less number of files are touched and needs to be updated. So, but on the other hand, if your outer join, the second scan, is actually rewriting the files is slow, then there are different set of techniques. Well, there are common ones like adjust shuffle partitions that again controls the parallelism. But sometimes what happens is that if you parallelize it too much, you can generate too many small files. Especially with partition tables, it can generate too many small files. For that, the solution, the knob we have provided is that you can actually reduce the number of files by enabling automatic repartition of the data based on the partition column before the write. Now, this is available as optimized write in Databricks Delta Lake, but we, in the next upcoming release of 060, which we will release tomorrow or day after tomorrow, well, tomorrow actually, 060 also has support for this automatic repartitioning of data inside merge before writing. Then if it's a full outer join, the outer join that you see, then Spark cannot do any sort of broadcast join. Spark doesn't support broadcast join for full outer joins. But starting from Delta Lake 060, it's possible that it may be a right outer join, and Spark in that case can do broadcast joins. And then again, you make if you observe that in the Spark UI that you are doing a right outer join by looking at the logical and the plans as Denny showed in the Spark UI, you can also get it programmatically as well. Then you can adjust the broadcast thresholds to make it broadcast a larger volume of data than what Spark default is. It also helps to cache the source table data, because you're going to do two passes on both the source and the target, especially on the entire source. It helps to cache the source table or a data frame. It can speed up the second scan, but it's important to remember that do not cache the target delta table. because caching the delta table can lead to weird cache coherency issues, because if the delta table updates, the cache doesn't, it all can lead to all sorts of confusing behavior. So generally don't cache the target table if you're going to update it. Anyways, we are kind of short on time, so I'm going to kind of squeeze through the common design patterns very quickly. So the common design patterns, Denny showed a little bit of that in his merge example as well, is deduplication during an ETL. In ETL pipeline can generate duplicates. You don't want the duplicates in your final data table. So if you write a merge query that only inserts only if the unique ID based on which you can deduplicate, only if it doesn't match, that means that row, the new row that you are being inserted is not in the table, judging by the unique ID, only then insert. So this is, again, another example of the extended merge syntax that you need not even specify when matched clause at all. You can only specify when not matched, then insert. So this is a kind of deduplication. Now you can optimize it further by well, the problem you will face is that it may scan the entire table every time to find out whether the unique ID exists or not. So you can optimize this further if you know that your duplicate data is going to come within only a certain time period. Like if you have only a duplicate data only over last 7 days and not older than that, then you can specify, inject that 7-day constraint as part of the match condition, and therefore forcing merge to only search last 7 days of data for duplicates. So these are optimizations you can do. Another common pattern is using structure streaming. Structure streaming, you may compute aggregates using structure streaming very easily. I have previous talks in Spark Summit and stuff based on structure streaming. If you can look it up if you want to learn more about structure streaming. But what comes out of structure streaming are essentially key value aggregates, which are essentially prime candidates for really upserting. And you can do that very easily. Structure streaming has this operation called for each batch, where for every batch of generated, updated key value aggregates, you can upsert that data into Delta Lake by calling this merge operation within the for each batch. Again, more details is there in our online documentation. Another common pattern is GDPR, which is very easy to do with delete and vacuum. You delete the user from the info table and then vacuum the table to ensure that it is actually deleted physically from the files. But there are, again, better ways of doing that. If you want to maintain the entire history of a user, then rather than relying on the table's history, you can store the history of the user explicitly by keeping all the previous records of the user in the latest version of the table using these sort of operations called SCD type 2 operation. Again, details, examples are there in our online docs. I'm not going to go into detail. Another extremely common pattern is change data capture. People often want to take change data from their OLTP databases and want to do OLAP operations on them without affecting their OLTP databases. So they want to take the changes made in the OLTP database and apply it to some table in the Delta Lake format, which is great for OLAP. So for that, again, the merge operation supports delete, insert, update, all in the same syntax. So based on your sequence of changes, you can very easily apply those changes from OLTP to OLAP. Again, a very common pattern we observe everywhere. Anyways, to end my talk, let's talk a little bit of the community and the ecosystem. We are very aggressively making releases almost every quarter, making significant improvements in terms of the connector ecosystem as well as the performance of very popular operations like merge and stuff. We are going to release something in the next couple of days. In 070, we're going to release Apache Spark 3.0 support, which brings a whole list of stuff like SQL DDL support, SQL DML support, support for defining tables in Hive Metastore, and all of that. And this connector ecosystem is really growing. There's online documentation on how to use Delta Lake with Amazon Redshift, Athena, Presto, Snowflake, and Hive. We just released a couple of weeks back, released a Hive connector where you can natively query Delta tables from Hive directly. So take a look at the online docs. We have a growing partner of ecosystem partner that has promised to support Delta Lake within their platforms, and a very large list and a very rapidly growing list of users of Delta Lake. Thank you very much. I'm happy to. We should answer questions now. Yeah.
Yes, absolutely. So we got about 5 to 8 minutes left. So let's dive right into questions. I'll ask them to you, TD, and you go from there. All right, perfect. So first question, does vacuuming improve performance?
I was actually typing down that answer, but I guess rather give it verbally now.
Exactly. I figured giving it verbally would actually make a ton of sense in this case. Yes.
So in most cases, it doesn't, but in some cases, because when you're querying the table using Delta Lake, because of the transaction log, it doesn't need to list the directories to find out which files to read. So it doesn't really matter from Delta Lake's point of view whether there are too many files in the directory for a very large number of versions or not. But in some cases, we have observed that with very, very long history, like that leads to millions, tens of millions of files, the storage system itself often starts to behave in a weird manner because it just slows down all file system operations. And this is true for even cloud storage file systems like S3, Azure file system and stuff. So with very large number of files in the bucket or in the container in case of Azure. So, and that is something that is beyond what Delta Lake or any processing engine can do. This is just all file system operations slow down. So it's not advisable to keep very large history involving that requires you to keep tens of millions of files because it will slow everything down that is beyond our control or control of any processing engine.
Perfect. And then related to, again, we're going to talk about the file system a little more just because there seems to be a lot of questions about that.
Okay.
Yeah. What about the file distribution after you do the updates and deletes, right? I guess the concern is that basically because we're adding new files, as we've been talking about during an update and delete, and we're creating the tombstone, I'll eventually be able to speak English. What about the file distribution?
So yes, what can happen is that as you're rewriting these files, you can get a small file problem that can lead to fragment. But that's where Delta Lake, you can rewrite the layout of the Delta Lake with transactional guarantees using these operations. In Databricks Delta, it is the optimize operation. In open source, you have this operation. You have this option called. You can do essentially no data change writes using data frame writes, by which you can say that I'm going to rewrite this partition of the Delta table by reading all of the data and rewriting it back with a much smaller number of files. Essentially, this, in terms of data frame operations, just read as a data frame, repartition to a smaller number of files and write it back into that partition. And there is additional support for an option called data change, set it to false, which means that it is telling the transaction log that there is no data that was changed, only data was rearranged. And that helps in actually that write operation to not conflict with any other actual data change operations. So again, all of this is documented in our online doc, so take a look.
Perfect. And just to add to exactly to TD's point, during the unpacking the transaction log section, we actually dived a little bit into that as well. So just speed up to the section where we talk about file compaction and also the notebook itself that's associated with that particular tech talk. We actually not only dive into it, but we show you just like we do here. We show you in a demo exactly how that works. Okay. All right. So I think that answers those questions in terms of in terms of file size and all this other fun stuff. A more fun one here. Hey, Spark support for Java, Python, and Scala language. Which one provides the best performance and why?
Okay. So in terms of Delta Lake operations like reading and writing, there is absolutely no difference between Spark, between Scala, Java, Python. In terms of what processing you want to do an addition on top of that, once you have them as data frames and stuff, that is where there may be slight performance difference between Python and Java. It all depends on, let's say if you're doing built-in functions like explode and stuff, then there is absolutely no difference because everything gets boiled down and code generated on the Java side, even if you're writing Python. But if you're doing UDFs, that's where the difference may arise because Python UDFs versus Pandas UDF versus Scala Java UDF, those differences can arise in terms of UDFs. But that is purely on the Spark side of things, whatever queries you want to do in Spark, that is independent of Delta.
Perfect. Okay. So I'm going to switch gears a little bit now. We've talked about the languages. Actually, no, I'm going to stay in the language just for this one quick answer. Can we use how can we use the table name in the SQL query as opposed to the Scala and Python syntax? You already implied it with the Spark 3.0, but I figured it was worthy of us going ahead and toggling that out again.
Yes, I can explain that in more detail. So Apache Spark in the 2.4 line or the 2x line before 3.0 does not allow any data source like Delta to really customize what gets written out to the metastore. For Delta, what we really need is that customization because unlike like Parquet tables or CSV tables and stuff, Delta does not rely on keeping the metadata metastore. Rather keeps all the metadata in the transaction log. That means that when you're querying or planning a query on a Delta table, it needs a certain amount of customization such that it should not, so that it can specify that I do not want all the metadata stored in Hive metastore, rather I want to use the metadata in a transaction log. That since before Spark 3.0, there were no APIs to do that customizations. That's why we did not, the OSS Delta Lake does not, working on Spark 2.4, does not support Hive metastore defined tables because we could not do that customization. But with Spark 3.0, we added all the necessary APIs by working with the Spark community very closely. We added all the APIs so that we can, the Delta Lake data source can do those customizations and therefore read from Hive metastore by such that given a table name, it can map it to just the location, ignore all the other metadata from the Hive metastore, just read the location. From that, go ahead and read rest of the metadata from the transaction log in that location, and then plan the query based on that. This customization will come with Spark 3.0, which the time frame would be probably, we can only guess because the Apache process takes, it's little unpredictable for such a major release. It will probably land somewhere between June and July, most likely. And as soon as Apache 3.0 lands, we will have a Delta Lake release, most likely Delta Lake 0.70 release on top of that.
Excellent. Okay, I think we only had time for probably one more question, so I'm just going to leave it at that. The question is, how does the connectors with Presto, or basically work when it comes to trying to read Delta Lake? Right? Does it actually read the Delta log itself to figure things out? How does Presto connect, basically?
Very, very good question. So there are two-part answer to that. One, so the Presto support we have added in the open source does not read the log. It rather reads this thing called manifest files. Again, all the details are present in online docs. What manifest files are is that it's basically a bunch of text files that contains the names of the data files, the Parquet data files that someone needs to read a full snapshot of the Delta table. So the Delta Lake APIs provide the command for generating these manifest files on a Delta table, which can then be read by Presto to read the to figure out what are the actual Parquet files that needs to be read to query the Delta table, and then accordingly query it. So Presto has inbuilt support for these manifest files. Now that's the open, so it doesn't read the log. Now, Starburst, Databricks and Starburst work closely to build a Delta Lake native connector that actually reads the log, and I think they just released it on their enterprise platform. So that would actually read the log directly to bypass manifest files and stuff and read the log directly to find out what data to read. And hopefully at some point of time, they will open source that.
Perfect. Well, hey, thanks very much. I apologize that we could not get in